So we're going to begin today by looking at this extension, and I'm just going to show you how you can organize it so that what you're being asked to do here isn't all that different from what you're being asked to do on Monday during class. We're just adding one little layer to it, one little wrinkle to it. And if you can understand where that wrinkle comes from, you can do any problem like this. So organizationally speaking, we are starting with molecules. And we're eventually going to get to grams of carbon. So we've got molecules of propane, C3H8. We want to turn it into grams of carbon. Now, the way to get from there to there, there's a lot of different ways that you can go. But they're all going to center around a couple of key ideas. I need to turn the particles into moles, and I need to turn the moles into grams. Those are the calculations that you learned how to do last time. So nothing different or strange there, just maybe a slightly different order of things. And that slightly different order comes in, how do I use that chemical formula, C3H8, to go between the idea of the molecule of this compound to the individual atom of this element. And where I'm going to choose to do this is actually right here in the first step. I'm going to convert these molecules into atoms first. And the process there is not that hard. 1.3 times 10 to the 23rd molecules of propane. And I want to turn molecules of propane into atoms of carbon. Now, what does that relationship look like? Well, it's actually not that complicated. I've got a chemical formula here. The chemical formula here says there are 3 carbons and 8 hydrogens in this molecule. So the ratio here is 3 carbon atoms for every 1 molecule. Now, I could go a couple of other different ways with this. If I were asked for the hydrogen instead of the carbon, I would say 8 atoms of hydrogen for every molecule of propane. If I was just asked how many atoms are in this sample, well, 3 from carbon and 8 from hydrogen would give me 11 total atoms. So my ratio would have been 11 atoms for every 1 molecule. From here, this is nothing new. This is nothing that we didn't do on Monday already. My molecules of propane have canceled out. Now I have atoms of carbon. And the next logical step would be to take those atoms and turn them into moles. And then turn the moles of carbon into grams of carbon. And these are the exact kinds of calculations that we did on Monday. To turn the atoms into moles, I need to use Avogadro's number. 6.022 times 10 to the 23rd atoms in 1 mole. And my atoms cancel out. To turn the moles into grams, I need a molar mass. 1 mole of carbon is 12.01 grams. My moles cancel. I'm left with grams of carbon. So I carry this all the way through 1.3 times 10 to the 23rd, multiplied by 3, multiplied by 12.01, divided by Avogadro's number. My calculator tells me this, 7.77798 grams of carbon. How many significant figures do I need to round this to? How many digits do I need here? Yeah, if you're flashing me the peace sign, you're correct. The answer here is 2. And the reason it's 2 is, again, we go back to our initial measurement. Our initial measurement has 2 digits in it, the 1.3. Now, all of our other numbers here are either exact, there are exactly 3 carbon atoms in every molecule, or they contain more digits than the 2 that I started with. And since rounding always is to the weakest principle, the weakest, least precise measurement, 2 is the number of digits in that measurement. So 2 is the number of digits we round to. So I'm going to round to the second digit here. So 7.7, I look and see that this is going to round up. So it'd be 7.8 grams of carbon. And so that would be my answer to this question. So if you find a problem like this, just understand it's the same thing that we were doing on Monday. Use Avogadro's number to convert between moles and particles, whether they be molecules or atoms. Use molar mass to convert between moles and grams. But if I need to convert between atoms and molecules, so looking at the element versus the compound, I got to use the chemical formula itself. That chemical formula gives me what I need to make that conversion between atoms and compounds, or atoms and molecules, elements and compounds. All right, any questions with this before we move into mass percent and empirical formula? All right, so the next thing that we want to look at then is we're just taking small step extensions of what we were looking at on Monday. So one of the small steps that we're going to look at here is the idea of a mass percent. Mass percents give us just an idea of the parts of whole. So if I'm looking at the mass percent of a given element in a compound, I can evaluate the mass of that element relative to the mass of the compound. Now, putting that into something that you've seen very recently, the lab that you just did had those components in it. Because I took the mass of my copper, and I also figured out the mass of the copper sulfur compound, whatever that was. Well, that mass of copper divided by the mass of the product times 100% gives you the mass percent of copper in your compound. And for that lab, we're using that as a way to evaluate our percent error. How good was our experiment? How good were we at actually determining the correct formula for the substance that we were making? Now, mass percentage is something that is going to come up a couple of different times. Mass percent is a very common way of looking at construction of solutions. We can also see mass percentage used for determining things like alloy composition, pharmaceuticals, how much salt is in your saline bag at the hospital, lots of different things. Use mass percentage as the way of expressing concentration or relative amounts. So if we were going to try to determine the mass percent of the individual components of a compound, the way that we do that is we do it from a molar mass kind of standpoint. So using the periodic table for magnesium, we would look at the mass of magnesium relative to the mass of the product, magnesium chloride, times 100%. Now, to solve this problem, I'm going to need to do a little bit of calculating. I need to know the mass of the magnesium, and I need to know the mass of the magnesium chloride. Well, the mass of magnesium, I only have one magnesium atom here. So molar mass of magnesium from the periodic table is 24.31 grams per mole. The mass of magnesium chloride, I would need 1 magnesium plus 2 chlorines, 35.45 each. So add those together, 24.31 plus 2 times 35.45, 95.21 grams per mole. So that goes in the denominator of this fraction, 95.21. And we multiply that all by 100%. Because the grams per mole cancel out, mass percents are always going to be unitless. So 24.31 divided by 95.21 times 100%. My calculator gives me 25.5330. Looking at how I've constructed this, however, I've got 4 sig figs in that numerator and 4 sig figs in the denominator. So I'm going to need to round this off to 4 digits overall. The 4th digit here is this 3, and we're going to round it down since the number next to it is less than 5. So 25.53% magnesium. For the chlorine part, 2 ways that you could approach it. So you could do the same thing where you go mass of chlorine over mass of magnesium chloride times 100%. What we have to keep in mind in this case is that it's going to be 2 times the 35.45 grams per mole in the numerator, because there are 2 chlorines in the product. Grams per mole still cancel out. 2 times 35.45 divided by 95.21 times 100%. Again, to 4 significant figures, 74.47% chlorine. So this would be the one way to do it. However, there is a simpler way. Recognizing that this compound is either magnesium or chlorine, If I know the percentage of magnesium, the rest of it must be chlorine. And so I could take that number and subtract it from 100 and get the same 74.47% as well. So that's especially useful if I have information about, multiple atoms being present. I can always do this kind of subtraction calculation for the last component. So if I have a compound that has 4 different elements in it, and I know the mass percents for the first 3, I can figure out the 4th one by subtracting those other 3 from 100 and seeing what's left over. Now, why this information is relevant to us has everything to do with the fact that one of the most common ways of getting data for empirical formulas is through analysis. And the analysis that usually gets used is something called mass spectroscopy. In mass spectroscopy, usually what happens is that you get percent compositional data. So you put your sample into the spectrometer, it tells you, okay, this much of it is carbon, and this much of it is silicon, and this much of it is whatever else is in there. And it also tells you the molar mass of the whole compound as a whole. And from that information, you can piece together what the empirical formula is and what the actual formula for the compound is. So let's get into that. Let's start by defining what an empirical formula is in the first place. So an empirical formula is a reflection of the smallest whole number ratio of each element relative to the other elements in the compound. We don't see this as often with inorganic compounds, things that are ionic in nature, things that are non-carbon based. But in the carbon-based world of organic and biochemistry, what we can find is that a lot of different compounds end up with the same empirical formula. And so because of that, when we do that kind of spectral analysis, it becomes important that we actually have to figure out both. We use the percent data to figure out the empirical formula. We use the molar mass to figure out the molecular formula. And we tie the two ideas together through a pretty simple process. But a common example of that is we've got 3 compounds here, each in increasing complexity. We've got formaldehyde, which is not only the empirical formula, but its molecular formula is exactly the same, CH2O on both accounts. We've got acetic acid, which has the same empirical formula, CH2O, but its molecular formula is actually double that. Here they're showing it just to keep things consistent as C2H4O2. We actually can write acetic acid's chemical formula in a lot of different ways. Most commonly for this class, we're going to write it as HC2H3O2, which is how it is broken up from an ionic standpoint, the hydrogen and the acetate ion. And then we've got glucose. Glucose is actually 6 of those repeating units, 6 of those empirical formulas strung together in this considerably more complex structure. But they all have the same empirical formula in common. And so it becomes necessary for us to not only be able to do an elemental analysis of it, but also to know its molar mass so that we know which one of these is present when we do that analysis. All right, so what does the process actually look like? How do I take mass percent data and turn it into an empirical formula? The process here itself is actually not that bad. It looks bad. That's a lot of text there. But the process itself is really not all that different than what we've been doing the last 3 days. The first thing that we need to do is we need to turn the mass from the mass percent. Now, the way to do that is, since we are dealing with percent values, all that we have to do is turn those percentages and just change their unit to grams. Percent means part of 100, right? So if I assume that I have 100 grams of that sample, I can turn whatever that percentage is into a gram value. Now, do we actually need 100 grams of this stuff? No, but we use 100 grams just because it makes the math work out a lot easier. So if I'm told that I have something that's 24.5% oxygen, when I go to do the calculations here, I turn that 24.5% into 24.5 grams. And then from there, now I've got grams, I can turn grams into moles easy. And that's what the second step is. The second step is to convert the grams into moles using molar mass. From there, this third step, we're going to divide the moles by the smallest number of moles. Why are we doing that? We're doing something called standardizing to a mole. So by taking the thing that is present in the least amount, we are saying, okay, that thing is now 1 mole. Let's compare everything else to that and see if we can get other whole numbers to come from that calculation. Otherwise, it can be really difficult to compare one element to another if they're all in these long decimal forms. Sometimes it's easy to see when there's a 2-to-1 ratio or a 3-to-1 ratio. Sometimes it's really difficult to know the difference between 6-to-1 and 6.5-to-1. Number 4 here is confusing, but I'll try to straighten it out a little bit. This is our rules for rounding. So when we work with experimental data, it's very often going to be the case that it's not going to work out to be exactly a whole number after we do step 3. What this is telling us is if we are close to a whole number, we should round up to the nearest whole number or down to the nearest whole number. So if I get 1.86 instead of 2, I should round that up to 2. If I get 3.91 instead of 4, I should round that up to 4. What we want to look out for are fractions. In particular, we want to look out for quarters, thirds, and halves. So 0.25s, 0.33s, 0.50s, 0.66s, 0.75s. If we do a calculation and we do that standardization and one of the numbers comes out to one of these decimals or really close to it, that's telling us that there is a relationship there that is not a whole number relationship. There's a fractional relationship involved in there somewhere. And so if I find one of these coming out, I have to get rid of the fraction before I can move on to the empirical formula. So if I get one of these quarters, the 0.25 or the 0.75, I'm going to multiply everything by 4 to get rid of the quarters. And that should shore up all of the whole numbers. If I get one of these thirds, a 0.33, a 0.66, a 0.67, I should multiply everything by 3 to get rid of the thirds. If I get 0.5, I should round it. I should multiply everything by 2 to get rid of the halves. Now, if we are looking at an extreme experimental kind of situation, like what you just did in lab, we're going to be even more generous with our rounding here. And the reason we're going to be even more generous is because copper sulfide comes in really 3 different forms. There's the copper 1 sulfide, where I've got 2 coppers for every 1 sulfur. There's the copper 1 sulfide or copper 2 sulfide, where I have 1 of each. Or there's a mixture of copper 1 and copper 2, where I end up getting like a 3-to-2 ratio instead. So if I get a half of something like that, that's a telltale sign that I'm on the right track there. But what that also means is that if I end up getting a ratio and it's 1.74 to 1, I'm going to round that up to 2. Even though that's outside of the guidelines that are given here, I'm going to do that for our example work there because our example work isn't as book tidy as a problem out of a textbook. And chances are, if you got a 1.75 to 1 ratio for your copper sulfide, probably just means that you didn't burn out all the sulfur. It should actually be 2 to 1. So with that experimental data that we're working with in lab, we're going to be a little bit more loose with our estimation and our rounding. And so what I was telling my lab students is it's either round to the nearest whole number, so round up to the nearest 1 or round down to the nearest 1, or if it is right there in the middle at a half, multiply by 2 and go from there. Otherwise, round up or down accordingly. And I would suggest the same thing to you, because the thing is, if you do it another way, if you take everything and multiply it by 9 and get CU9S11, yeah, your percent error is going to look great, but there's no such thing as CU9S11, and that's going to be your problem. It's better to be wrong from an experimental error standpoint, but have the right formula, than to have the wrong formula and have great percent error. Anyway, once we get to this last stage, we've got the number of moles as a whole number. That's when we turn the numbers here into subscripts to make the chemical formula. So let's put this into action. And let's take a look at an example problem. All right, we're told that we have an unknown organic solid. Its mass percents are here. We want to know what the empirical formula of the solid is. So in your notes and in the textbook, there is this nice little chart there that shows you, kind of the process that you run into. So going from mass percent to grams, grams to moles, moles to whole numbers, and then eventually to molecular formula. This spot right here, so between the whole number subscript and the ratio, this is where we would know our empirical formula. So for the problem that we're about to do, we would actually stop right here. So first thing that we need to do, convert the percentages into grams. So 75.73 grams of carbon, 8.74 grams of hydrogen, 15.53 grams of oxygen. Our next step turn these grams into moles. So we gotta use the molar mass. 12.01 grams of carbon in every mole. So 75.73 divided by 12.01 to 4 significant figures is 6.306 moles carbon. Now, it's going to be really tempting for some of you to want to round these off early. 6.306, oh, that's not that different from 6.3. Let me just round that there. That way I don't have to do as much writing. I'd really caution you against that because especially when it comes to fractions and finding appropriate fractions, we want all the significant figures that we can get so that we can actually determine if a fraction is present. The more rounding we do early, the more estimated all of our figures are going to be later. So as we get closer to the empirical formula, we're going to be able to take more liberties with rounding, but not in this initial step. For hydrogen, 1.01 grams of hydrogen in every mole of hydrogen. 8.74 divided by 1.01 will give me 8.65 moles of hydrogen. For the oxygen, 16 grams of oxygen in every mole. 15.53 divided by 16 is 0.9706 moles of oxygen. So we've completed the first few steps. This is as far as we got on Monday. To take it the next step, we need to compare the moles to each other. So we've got to divide by the number here that is the least. And that would be oxygen in this case. So we're going to divide each number by 0.9706. And so we're only taking the magnitude, not the unit here. We're only taking the number. So for oxygen, we now have a whole number, 1 mole of oxygen. For hydrogen, 8.65 divided by 0.9706, I'm going to get 8.91 moles of hydrogen. And for carbon, 6.306 divided by 0.9706, I'm going to get 6.497 moles of carbon. Okay, couple of really quick notes here. We've got one whole number. These two aren't really whole numbers. However, for the hydrogen, remember we talked about that idea of estimating and tolerance. Is this close enough to 9 that we're probably okay? Yeah. Yeah, remember the book said anything within 0.15 is good enough to round up or down. This is within 0.15. So we're going to turn this 8.91, we're going to round that up to 9. 6.497 is not good enough to round. Except it's not exactly a half, but it's really, really close. So here's where we're going to take a little bit of a liberty here, and we're going to say, okay, it's probably 6.5, not just 6.497. It's close enough that that's probably what we're getting after. Now, that still doesn't solve my problem exactly, but it gets us a lot closer. Because now I can look at this and say, okay, I don't have all whole numbers, but I've got close to whole numbers. I've got one fraction I need to get rid of. So to get rid of the half, I need to multiply everything by 2. So 6.5 times 2 is 13 for the carbon. And since I multiplied the carbon by 2, I got to multiply everything else by 2 along the way. So 13 carbon, 18 hydrogen, 2 oxygen. My empirical formula is going to be C13H18O2. So this is how we do it. This is what we need to do. Is we take our percentages, we turn them into grams, we get it into the moles, and then we do whatever manipulations to the moles are necessary to get them to all whole numbers in the end. Now, I'll know I'm on the right track if this formula is non-reducible. So there is no common factor between 13 and 8. In fact, 13 is a prime number. So I can't reduce 13 by anything. That tells us we're on the right track. All right. Any questions with this? Charles. Can you rephrase that? Okay, so if that is the case, go back and check your math. So if this is a problem generated by your textbook, if you find it in your homework, then chances are really good that the numbers are going to work out pretty neatly, or at least within these kinds of rounding boundaries. Now, in the lab, like I said, in the lab, we're going to have some more fluctuations here because we're working with real stuff. And sometimes things don't always work out as closely to plan as what we intended. And so that's a case where we just kind of take it on a case by case and we just work with what we have as best we can. But if we're talking about a problem like this, it should work out pretty evenly, or at least pretty close to evenly. And the rounding shouldn't be too drastic, which is why they gave us those parameters of the plus or minus 0.15. Yeah, go ahead. So usually we'll use the problem as kind of the clue in terms of how it's supposed to be ordered. So they gave us the order carbon, hydrogen, oxygen. So we're just going, we put it in that same order, carbon, hydrogen, oxygen. And usually for problems like this, that's the order. Now, otherwise, what we would look at is if there are metals involved, we would put the metals in front and we put everything else kind of on the backside. Or sometimes we recognize, hey, I've got a polyatomic ion here that's showed up, where maybe I do the analysis and I get N and O3, and I go, oh, that's nitrate. And so I can recognize that cluster and group it together that way. So there's really not a great rhyme or reason for the order here. When in doubt, just use the order that you're given. But if you do recognize a pattern in there, you can feel free to draw off of that pattern as well. All right, other questions with this example? Okay, let's take one look at a, yeah, I know that. Let's take a look at a question here related to molecular formulas. When we're looking at molecular formulas, we need to find what I call the multiplier. The multiplier, which I'm just going to call capital X for no good reason, is always going to be the molar mass of the molecular formula divided by the molar mass of the empirical formula. And where this becomes useful for us is the molecular formula is equal to X times the empirical formula. So for this problem, we've got an empirical formula of C13H18O2. We're told that the molar mass is 412.26. What is the molecular formula? Well, we know the molar mass for the molecular is this. What we need to do is figure out the molar mass of the empirical formula. So for that, it's 13 times the molar mass of carbon plus 18 times the molar mass of hydrogen and 2 times the molar mass of oxygen. And if you do that, 13 times 12.01 plus 18 times 1.01 plus 2 times 16, you get 206.31 grams per mole. My grams per mole cancel out. If I take that number I get 1.9983, which again, using our general principles of rounding, that's going to come out to about 2. So to find the molecular formula, the molecular formula is 2 times the empirical formula, C13H18O2. So it'd be C26H36O4. I just took that 2 and multiplied it by each subscript to get my new subscripts. Okay, so I've got a little bit extra for you. We didn't actually get to the in-class examples. I wanted to give you a chance to work on doing this on your own. We ran out of time for that. So what I'm going to do, there are 2 questions here in the slide deck. One of them is an empirical formula question. One of them is a question just like what we did here. Turn the empirical formula into the molecular formula by determining the value of the multiplier. I'm going to put those into your Top Hat assignments as homework for between now and Friday. So make sure that when you log into Top Hat to do that active question, make sure that you also get into Top Hat to do that as well. But before you do that, make sure that you also hit the stoplight question on your way out today so that you can get that participation point as well. And thank you for your attention today. I will see you on Friday for our proficiency and our one-day whirlwind tour of nomenclature. Have a good afternoon.